Hello, very good evening everyone. My name is Samir and today we will discuss the week 9 tutorial and that will help you out to solve the problem of this week. So the question number on the this week is there, and the question is: in a super heterodyne receiver with intermediate frequency f2, what is the frequency of the local oscillator corresponding to an incoming signal of carrier frequency f2? So in this question we have intermediate frequencies. Okay, so calculate try to find out the frequency of the local oscillator. Okay, I think it will be f1. In a super heterogeneous receiver with intermediate frequency f1, what is the frequency of the local oscillator corresponding to incoming signal of the carrier frequency f2? So there you have to calculate the frequency of the local oscillator. Guys, you have 2 minutes. After that, we will go for the solution. So in this question, try to find the frequency of the local oscillator. So now we will go for the solution, and answer is a T2 first 20 f1 plus f2. Okay. So according to the question, we have to calculate the frequency of the local oscillator. The frequency of the frequency of the local oscillator to an incoming signal of the carrier frequency is f1 plus f2. So A part is the right answer. So okay, question number 2 is T1 system is an example of. So we have 4 options. Option 1 is the frequency division multiplexing. B is the code division multiplexing. C is the time division multiplexing, and D is the space division multiplexing. So you have to tell T1 system is an example of that type of multiplexing schemes. It's very tricky question. Again, I am repeating the question number 2. Question number 2 is T1 system is an example of FDM, CDM, TDM, or STM. So now we will go for the answer. So T1 system is example of the TDM, that's known as time division multiplexing. The answer will be C part. Okay, that is a solution, or we can say explanation. T1 system is example of the time division multiplexing. Now we have a question number 3 that is also related with the previous one, and the question is bitrate of the T1 system is approximately. So we have four options. First, two options given in kbps, that is 1 and 16. The last two is given in gbps, that is a 1.354 gbps, and fourth is the 1.554 gbps. So please answer, and the question is bitrate of the T1 system is approximately. Again, I'm repeating the question number 3. Question number 3 is the bit rate of the T1 system is approximately. We have four options: 1, 16, 1.3544. D is the 1.554 Gbps. So answer will be B part, that is known as 1.554 Gbps. That is explanation. Bit rate of T1 system is approximately 1.554. Okay, let me check. Mbps or Gbps. Sorry guys, it will be Mbps. It's really 1.55, 1.544 Mbps. Okay, I think it's a typing mistake, and it will be Mbps. Okay, question number 4 is numerical questions. So question 4 now is consider a sinusoidal modulating signal MT is given at AM cos 50t, that is quantized using delta modulations. The maximum value of the amplitude AM for the no slope overlaid distortion corresponding to a sampling frequency is fs 200 Hz, and the step size delta is 1, delta is given 1. So there we have to calculate the maximum value of the AM. Condition is given that no slope overlaid distortion, we have to avoid it, and given that fs is given for 200 Hz, step size is given as 1. So as a hint, I'm giving you stereo condition, slope overlaid distortion. You have a few data, and then try to calculate to find the value of the AM. Okay, take your time and try to solve it. So again, I'm repeating the question. We have to find the condition, find the value of maximum value of AM for to avoid the slope overload distortion, and the sampling frequency is given at 200 Hz, step size is given 1, or MT is given at AM cos 50t. So try to find the value of the maximum value of AM. We have a step size and sampling frequency is given. Okay, now we'll go for the solution. As will be parted is 4. How it's come, then we can. So we have to. The condition is given: no slope overload distortion. Okay. So we already know the condition of the slope, no slope overload. But we will try to find the maximum value of the differentiation of the MT. That should be less than the delta by TATS. Okay. So delta TS is not given. We have to fix some frequency. So we can replace the one upon TS by the Fs. Okay. So we have to use this condition to avoid the slope overload distortion. So what is the message? Our message signal is AM cos 50t. Sampling frequency is given at 200 Hz and step size is 1. So just we will put all these value in this equations. Okay. So first of all, we try to differentiate the AM cos 50t. So as we know that the differentiation cos 50t is the minus sin 50t, and 50 will come out to the maximum. So max of small values, that is the 50 AM minus sin 50t. Okay, so its maximum value of this mod, it's come 50 AM because sine having the maximum value is 1, so 50 AM coming outside and should be equal to the delta Fs, and Fs is given as 200. Or we have to find the value of the AM, so it's will be delta into Fs upon AM. Okay, so delta into Fs upon 50. Fs is given 200, delta is given 1. Just put all these values and it will become 4. So answer will be 4. Okay. So answer is the B part. Now we have question number 5. Consider signal MIT which vary 1 to 5, band limited 4 to 4 I kHz. Is time division multiplex after sampling respectively at an IQ rate for each signal. The samples are then quantized using Mu-law quantizer with L equal to 1025 levels and binary coded using PCM. So what is the bitrate of the resulting digital information signal? So here you have to find the bitrate. We have a message signal MIT that's vary from 1 to 5. Okay, it is band limited, which having the frequency is 4 I kHz. Okay, for 1 it's only 4, for 2 put the value 2 and it's 4 is 16. Then you can put all the value from 1 to 5, and we are applying the time division multiplexing after the sampling as an IQ state. Then the samples are then quantized using the Mu-law quantizer with level is given the 1024 levels, and we are using the binary coded using PCM techniques for the coding. So we have to find out what is the bit rate of the resulting digital information signal. So you use the concept of bit rate. Try to find the concept of the value of the bit rate. Okay, so just try this. So we have to find out the bit rate. So as a hint, R is equal to Fs. Fs is given. We can calculate the MSFS from the message signals, and we have a L is given. To from there you can calculate the n number of levels. So try this. Suppose we have a 5 message signals and that having different frequencies. So if you want to calculate the over of such frequency, so you know how we can calculate the maximum, how we can calculate the frequency. From there you can calculate the fs. From using the L you can calculate the n, and that's where we can find out the bit rate. Okay, we will go over the solution. Answer will become 4.4 Mbps, and that is the solution. Okay, so as I told you, the first of all we have empty that mighty, that is varying on I is varying on 1 to 5 and band limited and having a frequency for I kilohertz, I square kilohertz is sample and the Nyquist rate. So Nyquist rate of the MIT is 8 I square kilohertz because Nyquist rate is 2 type of rates will come be 8 I square kilohertz. So total number of samples per second 8 into value from the I value 1 to 5. For 1 it will be 1, for 2 it will go 4, the 3 9, for the 4 16, and 5 for the 5 it's 25. So we will add them and multiply with that. It's come 414 to 10 to the power 3. So it's come. So we can see now we have a quantization level that is given the 1024. So from the just from the we will try to find out the n. Okay. So it will be 10 bit sample. Okay. So as we know, the total bit rate is RV is equal to n to fs. The fs is given 414 to 10 to the power 3, n is given 10. So it will become 4.4 Mbps. Okay. So the answer will be B part. Next, question number 6. Question number 6 is in the delta modulation, the distortions that arise when step size delta is large in comparison to a signal that is relatively flat, that is termed as. So again, I'm repeating for the question. Question they are talking about the delta modulation, and the distortion that arise when step size delta is large in comparison to the signal that is relatively flat. So you have to tell which type of distortion they are showing. First option is a small amplitude distortion and granular noise, strict overload distortion for the additive white Gaussian noise. Take your time and just answer which types of distortion being there. Okay, so answer will be, sorry, answer will be the redundant noise. Okay, so that is the explanation. So in the delta modulation, the distortion does that arise when the step size delta is large in comparison to the signal. That there is a relatively flat is represent a redundant noise. Okay, B part. Okay, question number 7 is, consider a uniform quantizer with a 25 to 26 quantization level and maximum mass sensitivity is 500. So what is the approximation quantization noise power? They are talking about the information quantizer with having a 25 to 56 quantization level and having the maximum mass sensitivity is 500. So please find what is the approximation quantization noise power. So there we have a 256 quantization level, 500. Just try to find the solution how we can do the approximation quantization noise power of the uniform quantization in the case of uniform quantization. Okay, so now we'll go for the solution. So we have a level quantization level that is 256. Next we have a maximum message amplitude that is 500. So we have to calculate the quantization noise power. Answer will be C bar, that is 1.21 dB. So that is the solution. So we have a 512 quantization level. So from there we can calculate the bits, number of bits. So that is a resolution of the R, that is log 2 to 56. That will become 8 bits. Okay. Now we have maximum amplitude of the message signal. maximum values of amplitude, that is 500. So we have to calculate the quantization noise power, that is driving lecture, that is minus 10 log 10 3, 20 log 10 and max minus 6R. Okay. So just put the value, use your calculator, from there you will get the values. R is 8, M max is the 500, so it will become 1.21 dB. Okay, so answer will be C part. Okay, next question number 8. Question number 8 is, consider a uniform quantizer with 64 quantization level and a maximum accessibility is 100. What would this the quantization noise power? This question is same as the previous. What we have to check there, now we have a maximum, we reproduce the quantization levels and we reproduce the amplitude messages. So use your intuition power and tell me what will the answer, what would be answer, what quantization noise power would increase or decrease, whatever. So just try to find the same concept whatever we used in the previous questions. Okay. As a hint, using the same formula, same way, try to find R and, sorry, so okay, try this. So answer will be A part. Okay, so formula is same. We have a 64 quantization levels. From there we calculate the resolution, so that will become 6 bit. Okay, maximum value of M is 100. Put all these three here. It will come in the minus 0.77 dB. So as we reduces the levels, we are finding that well, quantization noise has been decreases, and it's sorry, okay, so it's coming minus 0.77 dB. Okay. Okay, question number 9. It's related to super-heterodyne receiver. So question number 9 is consider a super-heterodyne receiver with broadcast frequency FC is 2 kHz and intermittent frequency is 1 kHz. So the corresponding local oscillator frequency that is larger than FC is given as. So calculate this. The corresponding. Again, here we get the broadcast frequency FC is 2 kHz, intermittent frequency is 1 kHz. So what will be the corresponding local oscillator frequency? Okay, so answer will be 3 kHz. So given is that FC is 2 kHz and IF is 1 kHz. So to correspond to calculate the corresponding frequency of the local oscillator, we use the FC plus FIF. So it's just put the value FC is 2 and FIF is 1. That will be 3 kHz. Okay, that become 3. Okay, question number 10 is what is the minimum bandwidth required in a time division multiplexing system to multiplex the samples of n signal? And each band limited to the FM. The question is we have n signals, each having the bandwidth is a FM, and we are applying the TDM system. So what is the minimum bandwidth we have to require? Okay. Again, I'm repeating the question number 10. After that, we will go for the solution to try this. Question is what is the minimum bandwidth required in a time division multiplexing system to multiplex the samples of the n signal at each band is limited to the FM? Now we will go over the answer, and answer is the A part, that is NFM. That is the explanation. So we are talking about the maximum bandwidth required. So the maximum bandwidth required in a time division multiplexing TDM system to multiply the samples of n signal. Sorry. Okay, that was explanation. Question is the maximum bandwidth required in a time division multiplexing TDM system to multiply the samples of n signal. So each band, and then there is given is there each band limited to the FM. So the maximum bandwidth will be NFM. The answer will be A parts. Okay, that was the last question of this class. Okay, so now we will end our class. Okay, thank you. There, in this question number 1, there is some typing mistake. I will overcome these issues in the PDF after I will upload it. Okay, so answer is F1 plus F2. Okay.